Hello everyone, my name is Yash Srivastav and I'm a co-founder of Tinsi Race Cars. In this video, I'm going to discuss the finite element analysis of an upright for Formula students, FSAE and BAJA vehicles. And generally it has been seen that finite element analysis is conducted by teams, but it is not always conducted in the right way. And it's very important to get accurate results. You have to simulate the exact practical conditions that any component goes through when it is performing at the field. Okay, so if you don't do that, then generally the analysis that you'll be doing will not give you accurate results. And if you have seen an upright or a hub or any component that you have worked on, which after doing finite element analysis, if you have seen it fail, then you can easily compare it with your finite element analysis model. Then if it is failing at exactly the same point where your FEA was predicting, then your FEA was accurate. Otherwise there were certain issues with it and you might not have simulated the exact field conditions for analyzing it. So uprights are normally the one of the most frequently tested or analyzed component by Formula student teams, and therefore I have taken this example to go with a Formula student upright. I have modeled a very simple upright to carry out this test, and I will be doing my calculations and I'll be doing my analysis on that upright. It's not a very good design, I would say, because it's quite heavy and it's quite over designed, as you will be seeing when the analysis will be over. But just to keep the keeps things simple, to keep the geometry simple so that you can easily relate to it, I've selected this model. So here's the upright that we'll be working upon. As you can clearly see that there are two suspension mounting points, one at the top and one at the bottom, and then there is a toe control. It can be a steering arm, or if you are working with rear upright, it can be the toe control arm. Okay, so we are assuming it to be the front upright at the moment, right? So this is our upright that we'll be working upon. Now you can also see that I have attached a hub over here. It is not the exact hub that I have designed for the application that I'll be putting this upright, where I'll be using this upright, but it's a dummy hub. You can see the name over here that I have also given to it is dummy hub. Fine. So now generally what happens is that when people work on the finite elements of upright, finite element analysis of upright, then either they constrain it at the center of the upright and apply loads at the suspension mounts. Okay, and right now I'm not talking about the braking torque, which actually you will be applying on your brake mounting bracket, but I'm talking about the longitudinal, the lateral and the vertical load that is acting on the upright with because of the vehicle. And generally either people constrain it at the center and then apply load at the suspension points. But actually if you see the real-time conditions under which an upright works, normally all the load that acts on the upright acts through the tires. Okay, so you have to really understand this situation very clearly. Suppose you're accelerating, at the same time you're cornering, and at the same time you are applying the maximum downforce. If you are using a Formula student vehicles, then of course you will be having some amount of downforce. So all of that is acting on your vehicle. Fine. Now we'll say I'll take 100% load transfer, 100% longitudinal load transfer and 100% lateral load transfer. So I can create a situation, a hypothetical situation, where all the load of that the vehicle is encountering is coming on one wheel. Let's suppose let's take any wheel for that matter. Let's take the rear right wheel. Okay, so all the load that the vehicle is encountering is coming onto the rear right wheel. Fine. Now when the load will be applied, I'll assume that the shock absorbers have bottomed out, and that is the point when the maximum load is going through the upright. Fine. I have to simulate these loading conditions to analyze my upright properly. Okay, so since I've taken 100% load transfer, so I'll say that 100% longitudinal load transfer, so all my load is coming onto, all the front load is coming onto the rear, and then 100% lateral, so everything from the left is going on to the right. So the entire weight of the vehicle is coming onto this one rear right wheel. Fine. Now let's say, like, the general practice is that for analyzing an upright, for longitudinal forces we generally take the forces as 2G. Okay, for lateral forces, again you take the forces to be 2G, and then to simulate the bump conditions properly, the vertical load, the maximum vertical load that you take is 3G. Fine. So all of that is actually acting initially at the tire, at the point where the tire is in contact with the ground. Okay, so this is the point which I have created, and this is the point where all the load is acting. Okay, now this is it depends upon what radius, what is the dia of the tire that you are using, and this is the hub, so I have taken 10-inch radius from the center. May vary for you. Okay, I have just taken an example. So this is the point where all the load is acting, and from here it will be transmitted through the hub, it will be transmitted to the upright. Okay, now how we are going to apply the constraints and the loads on this whole setup, that we are going to discuss next. So I have created a study over here, and you can see these pink lines coming up, and this is actually the way the forces have to be applied onto this setup. Okay, so many of you must be aware of that already, but if you are not, then this is the way how you have to apply all the forces. Okay, now you can see 3 arrows marked over here. So normally what people do is, it's an old practice that since all the time you're not having, you're not going to have maximum longitudinal and maximum lateral force acting at the same time. Okay, because if you are generating maximum longitudinal force, then at that point the lateral force will be very less. Okay, so you can't generate maximum of both of these forces at the same time. So what people do is they analyze longitudinal and vertical load in one analysis, and then lateral and longitudinal, lateral and vertical load in another analysis. But of course, you know, it's better to analyze the worst case scenario by taking both lateral and longitudinal forces, because anyways, if you are generating even a certain amount of longitudinal force, the tire is capable of generating some lateral force. Okay, so if you design it for the maximum, there's no harm in that. Okay, so obviously you are working with a race car, but if in an event like BAJA, where you also going through a lot of endurance, your vehicle is going through a lot of endurance, it's better to be, you know, on the safer side. Okay, fine. Let's talk about the constraints first. Okay, now see, before working on the constraints, I have two components over here. One is my upright, which is the area of interest over here. The other is the dummy hub. Okay, now since it is acting, it's this whole load is being acted upon through the hub, I have to have some contact between the upright and the hub. So I have given a contact. It's a bonded, no clearance contact between the hub and the upright. Okay, fine. Now let's look at the fixtures that we have over here. See, when you are talking about the suspension joints, okay, then what actually the suspension joints do? When the load is being acted upon, then these suspension joints, I'm just talking about the top and the bottom suspension joints, what they do is they constrain the upright in the in and out direction first. Okay, so they stop the upright from going in or out in the lateral direction, right? So as you can see, there's a green arrow pointing you know, outside, pointing in the lateral direction. So my upright at the suspension joint is constrained at in the lateral direction. Okay, so it can't go left or right. Same is the case over here. Okay, now okay, so this is the reference geometry 6 over here is the lateral constraint on both of these suspension joints, right? Fine. Now what is this other constraint? Now the toe control rod, it is also being constrained in the in and out direction. The other fixture that we have over here is again at the suspension joints, and they are constraining the upright in the longitudinal direction. Okay, so the A arms are also stopping the upright from going moving in the longitudinal direction, right? So I've constrained them over here as well. Then the last one is at the bottom upright, at the bottom suspension joint, and this constraint is acting in the vertical direction. Now suppose if you don't have this constraint, then you will be having a free movement. Okay, so here are the list of fixtures that we are having. There's another elastic support that we'll discuss a bit later. Now let's talk about the load. Now you can see there's a remote load over here. This is remote because it is acting from a remote point onto a particular component. Okay, so this is the point. As I've told you, it is exactly in line with the center, vertically in line with the center of the hub, and it is acting onto the surface of the hub, because it is this entire surface of the hub is contact with the rim. So it is acting on the surface of the hub, and it is 10 inch below the hub, below the center of the hub. Okay, you can see the 3 arrows. So let's look at the 3 forces that have been applied over here. Okay, right. So now, as we discussed earlier, that 3G for lateral force, we will be going with a force of 2G. Okay, let's suppose our vehicle is 300 kilos. Okay, so if we are having, suppose, a 300 kilos vehicle, then 2 into 10, a force of 6,000 newtons. Okay, in the x direction or in the longitudinal directions. Okay, and then a force of 6,000 newton again in the y direction, that is the lateral force 2G, and a force of 3G in the vertical direction. So then it becomes 9,000. So these values that I have used, they are recommended values for Formula Student and FSAE, and if you have been researching on it, you have been working on it from long time, then there are chances that you may disagree with these values, that why do you want to use 3G in a vehicle which will never be hitting that kind of force. Suppose you have that kind of if you are really sure about that, then obviously you can use your own values, but just for the sake of example, I have taken these values over here. So I have applied all the forces that have to be applied, and they are remotely acting onto the upright, right? Fine. Now let's come to the elastic support. The elastic support is there because if all of this hub, see, hub is bonded and it is also constrained to be concentric with this bore on the upright. So if all the force is acting, the hub will start rotating. So if it starts rotating, and if you analyze it like that, then it will be giving you large displacement error. Okay, you have been using SolidWorks FEA, and even in other FEA packages, you must be familiar that if your assembly is under constraint, then you will be receiving errors of large displacements, and then won't be possible to analyze it. So you have to have an elastic support. Elastic support, I'll just show it. Yeah, it looks like this. Okay, so I have given elastic support of 50 Newton per meter per meter square. Okay, and both normal and the shear. Right. So I have applied these forces and all these fixtures. So now my model seems to be ready for analysis. Okay, and it is already meshed, so I'll just show you the mesh that is there. Okay, so I haven't worked upon the meshing, it is just the autonomous meshing option that is available with SolidWorks that I've used. Okay, and let's now run the analysis and let's see what the result is. Okay, so the analysis is complete and I have the results with me. So these are the stress values that I'm encountering onto this on this assembly, And as you can see, the material that I've selected is AISI 1020 350 megapascal. If you have a better material, just feed in that material. And the maximum that I'm going is 250 megapascal, so it is obviously safe. And let's to be on the safer side, let's look at the factor of safety values. Now I've only analyzed the factor of safety for the upright because hub is something that I won't be interested in. And you can see the minimum factor of safety that I'm getting is 1.48. Okay, and it seems to be okay. 1.48 is a good value, and you don't want to be over designing your component anyways. However, there are certain things that you can improve upon. Particularly if I talk about this design, then obviously there are a lot of things that we can improve upon. And to check that, let's use a factor of safety probe and see the factor of safety values in various regions. Okay, suppose I'm looking at this. Now you can see that factor of safety is 25.52 over here, which is a very high value. Okay, you don't need that much factor of safety. And if you look at this point again, it's 11. Okay, so again it is a very high value. So we can afford to remove some material from over here and bring the factor of safety value down. At the same time, our weight will also be going down, so it's less unsprung mass, and we all know the advantage of that. Over here I'm having a factor of safety of 3.64, 4.74. so in these regions I'm having less factor of safety, but there are a lot of regions in which I'm having very high factor of safety values, and I can easily remove a lot of material from over there to make my design better, more optimized, and more according to the requirements. Okay, so this is actually the way you have to analyze your upright, and these are the constraints and the loads that you have to apply on it. Now this is not a complete analysis. There are a lot of assumptions that I have used. Firstly, I have assumed that both these A arms are exactly pointing in the I have assumed that both these upright, since I have constrained them exactly perpendicular to this plane, the plane that you're seeing the upright in at the moment. Like, if I look at the upright over here, right, like this, then I assume that exactly my A arms are parallel to the ground, okay, or perpendicular to the vertical plane of the upright. Okay, that's why I've constrained them exactly in this direction, in the vertical direction. So obviously it's practically, when you are installing an upright, when you're designing a suspension geometry, then that is rarely the case, almost never. You always have your A arms at a certain angle, so it's better you instead of doing it completely horizontally or vertically, you can constrain them in exactly the direction of your A arms. And how you can do that? So let's go to the model, and there are certain components that I have hidden. Okay, as you can see there, I have modeled also a ball joint. Okay, now this ball joint is actually the way this ball joint will be oriented is the orientation of my A arms. Fine. So what I can do is I can orient this thing in exactly the direction in which my A arm will be pointing. Okay, so once that is oriented, then instead of applying the constraints over here, suppose like I have applied, then I can apply my constraints on these nodes that you're seeing over here. Okay, and when you'll apply these constraints on these nodes, they'll be exactly perpendicular, okay, to the surface, and then you will be constraining your upright in the right direction, in the direction of the wishbones that you're having. Okay, so it's better that you do that. It's not just better that you do that, but it's actually required to analyze your upright with the maximum accuracy. And you can place 3 ball joints on the 3 suspension pickup points that you're having over here. And you can also simulate if you're having your shock absorber mount on the upright itself, where generally people have it on the A arms. If you're having on the upright, then you have to constrain on the on that bracket as well. Okay, And then another very important analysis for the upright is the analysis of the braking torque, which acts on the brake mounting bracket. Okay, so this is these are the points on which your braking caliper will be mounted at. But when you'll be analyzing it, then you'll be constraining your upright at the center, and then you'll be applying your braking torque on these two caliper mounting points. Okay, so to analyze the braking torque, you have to do this analysis as well for your upright. Then you can go for a stiffness analysis of your upright. You can calculate the natural frequency with the help of modal analysis. You can also go for frequency analysis. Then you can go for fatigue analysis, which is very, very important. So there are a lot of analysis that you actually have to go through. You actually have to perform on your upright to obtain the best suitable design. Okay, so it's not just the static analysis that we are seeing over here, but static analysis is a very good starting point for any design, because once you see the load paths and once you see the way your component is behaving, then you get an initial idea of whether you're designing it in the right way or not. Okay, and once all these things are finalized, once you have the basic design ready, then you can analyze it for for things like frequency, and for modal analysis, for fatigue analysis. Okay, so but the basic starting point is a static analysis, right? So I hope that this was a good discussion that we had, and if you think that you have certain doubts in it and you're not clear with anything, then please drop us an email or post your comments about this video. And if you want anything else on which we can make a video, and there are certain, because many people have asked us about this finite element analysis of upright, and that's the reason why I made this video. So if you think that there may be other topics in which you may be interested in, and please let us know about them, and we can make video on them as well. There are other videos that we have made on a lot of topics that may be of interest to Formula student teams and BAJA teams around the country, and you can watch those videos, and I hope they will be helpful. And that'll be all for this video. Thank you very much for watching this, and please subscribe to our channel to get to watch more such videos, and thank you very much.